Mm-hmm. It's not hard to. Yep. 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 Here. Well, you can, in the FM broadcast band spectrum, you can transmit a low power station if you aren't interfering. Yeah. Also, there's a. Hello, hello. Hello.
How do I pronounce your name exactly?
Skylar.
Skylar and last name?
St. Ledger. They're supposed.
Ligger.
Ledger. It's
Ledger.
supposed. Yeah, Ledger.
Ledger.
Yes.
Skylar St. Ledger.
Yes.
Beautiful. The last thing I want to do in introducing you is say the name horribly wrong.
Oh. As if you did, then I could correct you in it.
That is valid. Yeah, if I do, please correct me.
Hello. Test. Can you hear me? What? Raspberry Pi? Raspberry Pi? Mm. Well, actually, if you really want to launder money, I would recommend you open a fake laundromat. No one would suspect the laundromat for laundering money. A hack a day keeps the malware away. Their shirts are. What if it's free stuff? What if I throw a MacBook Pro at you? You might end up with a broken arm. Yes. Or better yet, if I throw a $2,600, like 50-pound Linux workstation at you. I think then I'd be more amazed that I could actually throw that. But oh, the black badge. However, I do think there is a fairly good arbitrage opportunity in get up really early, buy a bunch of passes, and then sell them to people stuck at the back of the line. Or go to corporations and say, I will guarantee you a DEF CON badge this year, because like they need it. Um, because it's yeah. Then, yeah. However, there is, I don't think so. Well, there are other reasons. It's not really hard to tell there's that person in a full suit and tie and everyone else is wearing a t-shirt. Previously, then before Snowden. Uh. It has a built-in microphone, right? Classified. We can neither confirm nor deny the existence of such information, and hypothetically, if such information were to exist, it would be classified. Who says he even worked for Apple? Okay. Yeah, I might have my watch. I can do that. Yeah. I'm good. Okay. Mhm. Yes.
Last year I spoke here on additional applications you can install for your Ubuntu desktop.
You could.
And I talked about all the ones that aren't in the repository files and it wasn't even use scrap, it was just Ubuntu scrap. I wouldn't. I hope I'm not. I hope we can find people who are younger than 23. I don't know. When do you stop being in your youth? I'll grab a picture of you.
Okay.
Ready? Every person is scared to see your picture now. I hope that's cool.
Yes. Or maybe not. Is that a good thing?
The only thing they can take from this picture is that you like red shirts, maybe.
Like Tom Scott?
Yeah.
I know. I realize I wear a lot of other T-shirts, but I've noticed I've worn this shirt at least I think one other talk I gave. Oh, I need to
Okay, when
press.
you're ready to start, you press
Yeah.
that and it'll switch to your
Okay.
something. I think it was at Target they did some case a few years ago, to where they were tracking this woman's purchases so much, and they have an algorithm to decide.
This is they knew she was pregnant thing. Yeah.
Where she didn't even know she was pregnant. Target.
Or I thought no, it was she did, but her father didn't and got upset when they sent her when he saw that she was getting coupons for like
Sure, so it was something like
yeah.
that, where they were able to detect so early that she was pregnant. It's like, which seems to be good. If there's any problems, then you guys just right? Yeah, we're gonna start in about a minute.
Period. There's a period space, but due to the registration thing, it didn't allow it. My dad put his
LEGE.
yeah, Saint Ledger, who was had his eyes gouged out and whatever.
No worries, I guess. Sometimes you can't win them all.
Doesn't everyone want their? Well, he was a martyr. Just
Valid point.
you kind of can't use the money from becoming a martyr since you're usually dead.
So are you plugged in? Because I see.
I'm gonna plug in now.
Do that. Make sure you get that up.
Mhm. Off. Okay.
All right, everyone, how are we doing today? You ready for the talk? Because if you're not, you should be. It's going to be amazing. So this is Skylar St. Ledger. If you've never met him, you certainly will for the next hour. Skylar, what are you talking about today?
I'm talking about software-defined radio and what you can do with it and why you care about it.
So if you are not here for that talk, you should
Stay here anyways.
Exactly. It's going to be the best talk. Absolutely. All right. Should we switch on over? There's right there.
Yes.
On, so
Here we go. Because you're not inputted into here.
It should go through here. Let's see, does this work?
So how's everyone's SCaLE going so far, though? Did you guys see the keynote today? What'd you think of it?
Okay.
Excellent. All right. So let him do what he needs to do. You guys go to the expo hall yet? You got to go to the expo hall. I went around yesterday. My T-shirt count is up to 23. I'm pretty excited about that.
That's more than CES. This should be good. Okay. And ta-da!
Here we go. All right. Let's give it up for Skylar here.
So as you already heard, I'm Skylar St. Ledger, and today I'm going to talk to you about software-defined radio and open source and why you care about it. So first I want you to think about how many radios you have on you right now. So you probably might be thinking none of them, but you actually, just in your phone, have 4 or more radios. You have cellular radio, Wi-Fi, Bluetooth, and GPS. When you go home and you click your garage door opener, that's another radio. You sit down on the couch, turn on your ceiling fan, that's another radio. Radio transmitters and receivers are all around you. You just don't notice them. But there's one thing that these all have in common that differentiates them from software-defined radio. They're all very specific. The radio in your phone has one radio or one subsection of a radio IC that just does Wi-Fi, another thing for just Bluetooth or just GPS. Your garage door opener, it just opens your garage. You couldn't use it to make a phone call or do something like that. Software-defined radio just goes, and it says instead of having hardware that can only do one thing, it then says, let's move that into software. It makes it where your hardware can do almost anything, and the limiting factor is the software that you write. Now you're probably wondering, what are good uses for software-defined radio? So commercially, there aren't that many big applications because software-defined radios tend to be expensive and they tend to be fairly power-intensive since what you could optimize in hardware, you now are all doing in software. But they're useful for military applications where you have to have a wide variety of different radio protocols that you're using, And for researching cellular 5Gen or 5G and beyond specifications, because you want to be able to very easily change the way you're transmitting or receiving a signal to research that. So with SDR, you still need some amount of hardware like this, but it's very minimal. The hardware is just the RF front end, which you're receiving is a low noise amplifier, and some filters and a mixer, and then that goes into an analog to digital converter to send it to your computer. To transmit, you have pretty much the reverse, a digital to analog converter, which goes through some filters and whatever, and then out in an amplifier out to your computer or your antenna. So this is a traditional radio receiver. In this case, it'd be AM radio. And you have your antenna in here. It goes through an amplifier, a mixer that shifts the frequency down to something that's easier to work with. Then it goes through some more filtering and amplifying and is demodulated. In this case, this would be AM radio, so it takes the amplitude of it and then puts it out to a speaker. This is pretty much what an AM radio receiver would look like with software-defined radio. The difference is that right about here, you then end up, this is all done in software, the demodulation and the audio part. You still have some of the hardware to receive it because you need hardware, but there's a lot less of the hardware, and you can change it much more easily because you're doing everything in software. So as far as hardware goes, there's a whole bunch of hardware to choose from. This is by no means a complete list. These are just some hardware that I know of and either think is cool or is cheap. The cheapest one is the Realtek RTL SDR dongle. This runs you about $10 to $20, $30 on the high end. What it started out as actually a TV tuner dongle, and someone found out that you can get it to dump the raw data to it. Now, you do get what you pay for in that this has a higher noise floor, which is what is the quietest signal you can receive and how much effectively static you have in the background. And also, it only has about a 2 megahertz bandwidth, which means you can only look at a fairly narrow portion of the spectrum at any one time. There are things like the FunCube Dongle Pro Plus, which is a higher quality one. These two are both receive only. Everything else here can receive and transmit. The Hack RF1 and the Blade RF are probably the two most popular ones. These software-defined radio hardware transceivers are both open source. Software-defined radio has about a 20 megahertz bandwidth. The Blade RF goes up to, I think, 40 megahertz. And then there's the USRP, which is made by Edis Research. These are like the commercial, really nice ones, and these are open source as well. The UMTRX is cool because it uses the same hardware transmit receive stuff as the Blade RF, but it has two of them. So you can be transmitting on one frequency and a different frequency and then receiving on those. There's also, the important part of software-defined radio, is the software. So if you're stuck on Windows, I feel bad for you. You can use SDR Sharp and HDSDR. SDR Sharp is closed source freeware. I believe there are older versions that were open source. It's written in C Sharp. And you can use it because it's nice because it installs all the drivers for you. If you're on Unix, Mac, Linux, one of those BSD, GNU/Linux, whatever you want to call it, operating systems, you'll usually end up using GNU Radio, which is a framework for taking samples and data from your radio, then passing it to different modules to do processing on that, and it takes care of all the timing and making sure that the data gets where it needs to go. GR Osmo SDR provides hardware drivers and interfaces to GNU Radio, so it makes it really easy to connect this radio to GNU Radio or any other radio. And then on Mac and Linux, there's GQRX, which is a nice piece of software just for browsing the spectrum. There's also software for Android, which lets you either connect either Hack RF or Realtek dongle to your phone using a USB on-the-go adapter, and you can view the spectrum that way. And there's also an ADS-B receiver, which I'll talk about more. So now we're going to get into some demos. You're all supposed to be excited now. Yeah. Hopefully they don't break. If they do, it's your fault. So let me change my display. Nice thing about running a Mac is you don't have the display issues that you normally have with Linux. Okay. So this is GNU Radio Companion, and this makes it easy to prototype and do SDR software. And what it will let you do is, it effectively lets you make a flow graph type thing. So what you have here is a flow graph that's fairly simple. And what it does is it takes the radio in. It'll then show you an FFT of it, which takes the radio signal, which samples it over time, and it will then convert it to frequency. And it then multiplies it by a sine wave to shift the frequency down so it's centered. It then filters it and will put it out over audio. So this we can use to listen to an FM radio station. Now, one thing you need to do for this is you need to find the radio station. So to do that, there's this nice piece of software called Osmocom FFT. And if you have a GPU in your computer that's supported, you can use this thing called Phosphor. And what Phosphor will let you do is, so this is loading the software on my radio, and it will work. And what Phosphor will let you do is it will use your GPU to accelerate the processing of the FFT, so you get a really nice looking waterfall spectrum view, which will open. So this is it. So first we want to turn up the sample rate, 20 megasamples per second should be good, and turn up the gain, and let's see, make this bigger, there. So what we're looking at now is the FM broadcast band, and I should turn up the gain a bit more. Actually, longer antenna. It helps if your antenna is tuned for the wavelength that you're receiving. So FM is, or at least in this, it's fairly low frequency, so you'll want a longer antenna. Frequency tends to be very relative. For some stuff, a few hundred megahertz can be high frequency. For other stuff, a few hundred megahertz is very low frequency. So what we're looking at here is we're seeing, actually I need to set it to the right antenna port. One other thing is some software-defined radios have multiple places you can connect an antenna. Make sure you choose the right one, or else you'll wonder why things aren't working. Or X, there. And anyways, with this you can look at the FM radio spectrum, and this should work. There. So now this should work better. So a few things here. There's your sample rate, which is how many samples does it take a second. In this case, it's 20 million. And a sample is actually a pair of numbers. It samples it as a complex number, so you have the real and the imaginary portion. So this is much better. So if we look at this here, what we'll see is there are, so each of these peaks here is where there's a RF energy present in the spectrum. In this case, we're looking at the spectrum from 90 megahertz to 110 megahertz. So this is the FM broadcast band. And if we look here, we'll see here's a station, here's another station. And because of the GPU acceleration, you can actually see the colors. The coloring here is telling you effectively where the signals spend the most time. And then down here, you can actually see the audio data as it's being modulated. So with FM radio, it's frequency modulated, so the frequency will vary. If we zoom in on a station, which you can do by tuning to, let's see, 100 should be good. And let's go to 6 megahertz bandwidth or sample rate. There. So if we look in here, we can see some of the stations more clearly. And let's see, this 97.7 should be good. One other important thing to note is that you'll typically get what's called a DC offset, which is where, due to the way the sampling on here on the radio is done, you'll end up with there will be a peak at 0 because it shifts the frequency down and there's usually some offset there. So just make sure that if you're trying to receive something, you ignore that effectively. So if we look here, you can see here is a radio station, and you can see the voice data that's being modulated. Here's another one. FM radio stations are nice because they are really high power, so you can receive them pretty much anywhere. Some radio stations will have what's called HD radio, which I don't see any here that have it. But if they do have HD radio, what you'll see is that you'll have the voice data in the middle, and then you'll see these two effectively square peaks around the edge. And those are digitally modulated audio data. And that if you have an HD radio receiver, it can demodulate that and give you voice from that. So you'll get like HD1, HD2, or whatever. And the cool thing is, the way it's modulated, if you have an old radio, as you tune across it, it just sounds like static. But if you have a radio that can actually pick it up and receive it, you'll hear the voice data. So now if we say, let's say you want to listen to the station at 97.9 megahertz, we can go over here and say that our station is at 97.9 megahertz. And now this should work. We need to close this and run. So GNU Radio Companion will take your code and decide it doesn't like it. So, yes, much like other GNU software. So, what it does when it works, which I think it will work, X ports and stuff on a Mac can be pain. Let's see. Can we hear this? That's static. Yes, that's... Okay. So if this works, sample rate, center frequency. I might need to turn up the gain. And this is why software-defined radio usually isn't used in commercial applications. It doesn't work. Also, like my fan on my computer is going, okay, here. Let's see. Is the audio on the VGA cable connected to the sound? Let's see. So no. So I'll just have you listen. Junior. That's a Spanish radio station. So you can do that. Right now it's using a bunch of CPU because that's a lot of work to process all this. Another thing you can do is you can actually demodulate what's called RDS, or radio data system data. And that is in FM radio, you'll have data that's, once you demodulate the data, you'll get, or the modulated signal, you'll get audio data. Except there's actually a lot more. So human hearing goes from about 0 to 20 kilohertz. They transmit about up to 15 kilohertz of audio frequency. Then there's a bunch of other stuff. So in that is the lowest part, the 0 to 15 kilohertz, is the left plus right audio, so that's mono. And above that, you'll have the left channel minus the right channel. The reason they do that is for your radio to receive stereo, it adds them and subtracts them to get the left and right channels. And by using that, you can then get stereo. But if you have a really old radio, it just picks up the mono audio. There's also some stuff that will give you information on what the radio station is, and this is called RDS, or radio data system. And this is how on your radio in your car it says, this is whatever radio station, and you're listening to whatever song. This runs, and it will, if we tune it to that same station and turn up the gain. And so what you see here is that there's actually a slight offset. So if we do 0.8, see. Let's try and find another station that might come in better. So when this works, okay, that was a comma. I'm guessing I probably need to turn up the gain more. Yeah. So it should be, actually that's what it is, the antenna. So the problem actually is the same thing I had earlier, in that the antenna is set to the wrong thing. I don't usually listen to the radio, and I usually really don't do this for reasons like this. No, it was using the so that's actually how strong FM radio is. Instead of using this antenna, it was using the other port, and that's why you're getting nothing now. So there, now I can turn up the gain, and this should come in better. So this station doesn't broadcast RDS, and also let's see, is there a way to see that? What is the grid position? GNU Radio is a pain on small screens because apparently, according to them, small screens don't actually exist. So you'll end up with, like, it's off the bottom and you can't see that part, which is always fun. And this doesn't like that breaks stuff. There. Does that work? No. So, let's see. So if I can get this to show it off to the where you can see it, you can see there at the bottom it shows the like what station is, like that's what I want. 5. Trying to remember. Let's see. So if you can move that down, now this should work. And of course, the configurations is like, here are 4 numbers that you know what all the docks are, right? Okay, this is not helping. Move that down. The other one just needs to be moved up, which is down here. GNU Radio flow graphs can get quite large. Yeah. So let's see. Put this one down. And now, if you move this one, oh, yeah. Nice thing about GNU Radio Companion is it will tell you if there's an error before, like, everything breaks, and it'll usually be fairly helpful. And also, you don't need to, it takes care of a bunch of the stuff and for you. The interesting thing about GNU Radio is it's actually, while it generates, so here you can see this now. So that worked. So this station doesn't broadcast it. You said 104.3. I can type. I do not want gigahertz. Okay. So if I can find, okay, so here it is. So what you're seeing is this is the data coming in from the station, and RDS is a fairly low bit data rate system. I think it only is a few thousand symbols per second or something. But if we look, we can actually view the constellation. And the constellation is effectively it's saying, like, on the X and Y axes, or sometimes it'll just be one axis, this is how the data is being sent. And every sample is plotted as a dot. So, like, if it's AM radio, you'll see one line, and you'll have dots everywhere it's sampled. In that line will represent the amplitude. In the case of frequency modulated radio, this would be frequency. I don't remember exactly what RDS uses, but when this is nice, you'll have two clusters of points. In this case, it's not receiving the signal really great, so you're getting kind of this all over. But the idea is you'll get it, and then you can look at the other things. This is the audio. It goes to about 15 kilohertz of left plus right. Then there's this pilot tone, which tells your radio receiver that it's doing stereo. And then further up on and this is an audio frequency now, you'll have other things, like there's some other data. This is RDS, and then your left minus right audio. And it's done as a double sideband audio thing. And then here's your RDS data, which works decently well-ish. So that is one use of software-defined radio. Another use for it is you can actually see what's called ADSB. And ADSB stands for Automatic Dependent Surveillance Broadcast. And this is used on airplanes so it's part of the FAA Next Gen program, and it's designed so that instead of just having the airport's radar get radar reflection off the metal body of the plane, and then it asks the plane's transponder, what are you? The plane will continually broadcast its location, altitude, and airspeed. So you can receive this very easily. You can actually receive it using this is an RTL SDR dongle. And these things are actually quite amazing in what you can receive with them, considering how low cost their construction is. One other nice thing is if you buy one and have a soldering iron, it can be helpful to shorten the antenna lead just so it's not as unruly as it is otherwise. But there's some software called Dump 1090, and that will allow you to do. It's called Dump 1090 because it's the signal's transmitted on 1090 megahertz, and this will allow you to receive it. And if you do --net, it'll allow you to do it over a network interface, which you can view when this loads. So this is receiving the data, and if once and it sets up a server, so you should be able to receive signals once this loads. Actually, oh, that's what it is. Wait. This. That's net. Yeah, it should be 8080. This was working earlier. Connecting. Fun is this? No. Let's see. So this should work. So when this works, you can see airplanes and where they are. It's so if you wait it so anyways, what this does when it does work is you'll see actually airplanes on a map if they broadcast their GPS coordinates, and you'll then see that like you can actually look at like where they are, how fast they're going, their airspeed. And the cool thing is that you don't need to transmit, which is good because you don't need a license or anything. And also, if you can't transmit, it's much harder to get in trouble. There isn't, except for a few things like pagers, there isn't really, you can't really get in trouble for receiving a signal. With radio, you always should make sure that if you're transmitting, you are licensed to transmit, and you're transmitting on the right frequency, and you aren't doing anything illegal. At SCaLE, there's a ham radio licensing thing, which if you want to get into this, I would advise that you do. And it's generally a good idea to make sure that you know what you're transmitting and where you're transmitting it before you transmit. Using something like GNU Radio, you can actually do a lot of the stuff all in software and not need to go into hardware unless you actually want to transmit. So some other things you can do with, I'll leave this running and see if this comes up with anything. So so GNU Radio and a lot of software-defined radio, it will use what's called complex numbers to sample it, which it's done because it makes the math a lot easier. So for AM radio, what you'll have is you have a waveform, and its amplitude will change based on how the signal it's modulating. So a very easy way of receiving it is just to kind of average over that signal and do what's called an envelope detector, where you say, what is the amplitude? The problem with that is, though, that when you're doing that, you then need to be able to, the frequency of your signal needs to be high enough that when you average it, you can still hear what you're doing. If you use complex numbers, which it effectively is, you have a pair of numbers, you can then do, where is it? Where did I save this? Okay, here it is. So you can actually, so if you use complex numbers, what it ends up doing is in the radio when it samples it, it mixes the signal and shifts it down with two sine waves that are out of phase. So one sine wave will have its peak here, the next sine wave will be over 90 degrees. And what it will do is you'll get two different signals from that. So one is called I, which is the in-phase or real signal, and the other is called Q, which is the imaginary or quadrature signal. It's wonderful that they chose I and Q, and I is the real one, when in math, I is the imaginary constant. But it is capital I, because that is totally an easy-to-discern difference. So with complex numbers, what you'll end up happening is when you look at like just the real or complex portion of it, it's effectively looking at the side. So this here is showing what's called phase shift keyed signal, which is where you have a sine wave, and the amplitude doesn't change, the frequency doesn't change, but what happens is the phase change. So it's effectively like it's going up and down, and it shifts over when that happens. So you can look at it here, and you can receive that fairly easily. But if you look at the different, like if you effectively change where your real plane is, it can go away. So if you look at it from this plane, you don't see that phase change at all. So, but using math, which is fairly complicated and a pain to understand, and Wikipedia is horrible at explaining complex mathematical ideas, you can turn it into a complex number in which the amplitude is actually the distance from the center of the circle. So if this was voice or AM modulated data, you'd look at the distance from the center here, and you would see that you'd have this wobbling around here showing when it's closer and it's lower amplitude, when it's further out it's higher amplitude. For the frequency is represented by how fast the signal goes around the circle. So the faster it is, the higher frequency. So for FM radio, you could then look at how quickly does it rotate around the circle. For phase shift keying, you can look at which direction does it go, and when there's a phase shift, that direction changes. So complex numbers make this math a whole lot easier because you aren't dealing with, okay, so if I average out this for AM radio, or trying to measure the distance between peaks in FM radio, or trying to keep track of the phase as much in phase shift keying, you can just look at it as a complex number. So there are many, many, many other radio modulation systems. AM, FM, and phase shift keying are probably the most common ones, but there are many other ones. A common other one you'll see is Gaussian frequency shift keying, so frequency shift keying is where you change the frequency of where you're transmitting. So you'll transmit usually a single tone and you'll just vary its frequency really quickly. The Gaussian part is just it does some shaping of the signal to give it better transmission characteristics. When you're transmitting a signal on the RF spectrum, there tends to be a lot of noise and interference and other stuff. One of probably the biggest sources of that is in 2.4 gigahertz, you have Wi-Fi, and Bluetooth, along with a bunch of other proprietary RF things like wireless mouse and whatever. Those can... What? Yes, and they'll also interfere with each other. So they'll end up... Let's see, is this... Okay, there. So what you'll end up wanting to do is design a modulation that's really robust. Okay. What is the... So this isn't picking up any planes still. If you have multiple devices connected at once, it can be kind of finicky to get them to all work. The easiest solution is just unplug it. But so there are all sorts of modulations. In another really, really busy portion of the spectrum is 900 megahertz, which it's also in what's called an ISM band, or industrial, scientific, and medical. And what an ISM band is effectively anyone can use this band, provided you follow some rules. Those rules are you're limited by power and a few other things like there's some limitations on how much of the spectrum you can use at once and whatever. But if we go to the 900 megahertz band, let's see, sample rate, turn up the gain, and I need to set that to the other port. TX/RX. And there. So if we go up to 900 megahertz, so we'll see a whole bunch of stuff. This is actually fairly interesting. So if you see, so what we can see here is there's a whole bunch of stuff. So if you look, there's usually digital packet radio stuff in here. This stuff here, I'm guessing, is probably interference from something. One thing that's interesting is your display in your computer, because there's often a digital interface. In digital, you have a square wave, and the square edge of that wave, it effectively goes up to an infinite frequency, because when you have any signal can be periodic repeating signal. Except if you just send that period out to infinity, then you can make it any signal. Can be represented by summing a bunch of sine waves at different frequencies and different amplitudes. And a square wave, because it goes up really quickly, how quickly that edge rises determines the maximum frequency of that. So in like the interface between your laptop and its display, you'll usually get a signal generated that, if you're careful, you can actually kind of receive and see what's on your display. It's hard to do, and I know someone tried it and they were mediumly successful. Very interesting. So this is probably some noise like that. But if you look here, so up here at around 930, 929 megahertz, these are pagers. Down here, this is probably a lot of the stuff 900 megahertz is digital modulation, so this is something actually, for this, shortening the antenna helps because it's higher frequency, so you'll end up with a shorter wavelength, and you'll want your antenna matched to your wavelength. So if we look here, this very quick bursty stuff is a digital modulation. It's using it's probably using a technique called it's a wideband modulation, in that it goes from, I'd say, about 5 megahertz wide. It does that so if there's a signal in the middle that interferes with it, it's more robust against it. And if you look how it's some very short, quick bursts, that tells you it's probably a digital thing. You'll see there are some, the lighting's not the greatest here, but there are some other bursts here. And that's all using this fairly limited of about 20 to 30 megahertz portion of the 900 megahertz spectrum. You have a question? I think so. I'm not entirely familiar with all the spread spectrum stuff. It could be. Direct sequence spread spectrum is a fairly common one, I believe. If we go down to about 800 megahertz, what we'll see here is more stuff. This is probably a cell tower, or is that, yeah, we're around 800. I'm guessing this is a cell tower. They tend to have around, you see cell towers around 800 megahertz, I think then like 1,800-ish megahertz. 1.9. If we go further down, we can actually see a TV station. TV stations in North America use a modulation scheme called ATSC, which stands for, I don't remember what it stands for, but that what it does is it takes an MPEG transport stream, then modulates it and transmits it out RF, and then it puts a carrier or a pilot tone that is fairly easy to see. So if we look here, it's also 6 megahertz wide, which makes it fairly easy to identify. So if we look here, this is probably, see this, we probably want the antenna a bit longer. So over here, this is probably a TV station. So we look here, let's turn up the gain. So we'll see that here's the pilot tone at 648 megahertz. Then at, let's see, at 654, which is about here. Actually, wait, that's actually probably not one. Let's see, or is it 4 megahertz? I'm trying to remember. So anyways, there's a whole bunch you can see. On the FCC website, you can actually view the licenses for TV stations. One cool thing about ATSC is that the channel number does not correlate to the California. Does not correlate to the yeah. So there's a virtual channel number, which is what you see, and then there's a channel it transmits on. So you could have something that's like channel number 2, but it's actually transmitting on what would be the channel number 38 or whatever. This is done to make licensing and sharing the spectrum easier. See, that should work. I want. You were on channel 43? I was? Yeah. Okay. 644 was the pilot. The video yes. Was, okay. 1 meg from 644. Okay. No results. Okay. So here you can see a bunch of stations. This loads. I'm surprised this doesn't have more. Okay. So we can see that this is on channel 5, which is Wikipedia has a nice list. North American television frequencies. If we go down to channel 5, that is on 76-ish megahertz. So due to the way the FM's or the broadcast bands have gotten divided up, you have the low channel, which is between 0 and 14, or channel number 0 to 14, which is everything which is VHF, or very high frequency. Then you have much higher channels, I think started around 500 megahertz, that is UHF, or ultra high frequency. And that's the rest of it. Let's see, 12 is, so in this case, it's channel number 12, and their virtual channel isn't filled in. You'll sometimes see, so here you can actually see there's the, yeah, so if we look here, I'm going to guess this is probably a station at 200 megahertz, or let's see. So it can be sometimes hard to tell. ATSC is you can find a station. Do you know of a strong station near here? Okay. Okay, so here, that should be the pilot signal. So what you're seeing here is here's the pilot signal, which is offset slightly to 210.31 megahertz. And then up around here, this portion here, you're seeing the actual data that's being transmitted. And ATSC, you'll actually see that it's fairly finicky, and that if how wide is it? It's 6 megahertz across the whole thing. So from 210 to 216, except you're getting a bunch of other stuff. So this here actually, what this here is, this is the, wait, you can't see that, or you can see it decently well. So this is probably the wireless microphone I'm wearing, and it's actually, okay, maybe not. So this is some wireless, okay, I think it's a wireless microphone, but what's happening is this isn't what the signal it's transmitting on. What you're getting is out-of-band transmissions, and that you either have this is either getting interference from it because it's really close, so it's interfering, or what you're seeing is that the microphone has some spurs or harmonics, which is, it's trying to transmit at whatever frequency it's transmitting at, I think 500 megahertz. Yeah, you're getting harmonics, so you try and filter it out, but some stuff leaks through. So if you're over there, you won't receive it, but really close, you're receiving it, and that's what this probably is. You'll also see there's a bunch of digital bursty packet stuff here that isn't part of ATSC, and that's something else. So effectively, RF is it's like being in a bar where everyone's shouting, and you're trying to have a conversation with someone. This is why you have organizations like the FCC who license it and try and help with this. Don't get them mad at you. If you're transmitting, know where you're transmitting on. Listen first. Make sure there's nothing there. Make sure there's nothing there. And then when you're transmitting, use the lowest power necessary, because a person 2 miles away doesn't need to hear you if you're transmitting in your own house. I think that's about all. Does anyone have any questions? So okay. How large is the slice that we're looking at? So the RF spectrum goes from, depending on how you define RF, a few hundred kilohertz up to hundreds of gigahertz. What we're looking at is, I think, 10 megahertz wide, 208 to, 10 megahertz wide. This radio, the USRP, can go up to, I think, 60 megahertz wide. Let's see, it can do up to 60 megahertz or 54. And so right now we're viewing a fairly large portion of the spectrum. These O's here are actually saying there's a buffer overrun, in that we're getting more data than we can process. But here we're looking from 186 megahertz to 240 megahertz. Depending on what you want, so like FM radio has about, I think, like 500 kilohertz is about as wide as it goes. And then you have wideband signals like Wi-Fi that's either 20 or 40 megahertz wide.
Does anyone have any additional questions?
This is the B200. Full disclosure, I visited them and they gave it to me. I also have a Blade RF as well. If you want to see it later, you can come look at it. The USRP B200/B210, the only difference between those is the B200 can receive and transmit on one, it has one receive and transmit port, or can receive on one frequency and transmit on the other. The B210 has twice, so it can receive on two different frequencies and transmit on two different ones. The Blade RF can receive on one and transmit on another one at the same time. These are what's called full duplex. The Hack RF is half duplex, and you can only transmit or receive on one frequency at a time.
Is there any other questions anyone might have? Just raise up your hand. I can hand you the mic. Here.
Are you licensed?
I have a ham radio license,
Good.
yes. In addition, I would like to remind everyone, don't sue me.
I have kind of a non-technical amateur question, but when I move around the house at various times, it interferes with the, my FM home radio, and also I notice there occasionally it seems like at certain points in the room, the hair will stand up on my arm. I swear it happens. I don't know if that makes sense, but can you explain that kind of what's actually happening in the house when you're getting that type of?
I don't know what's actually happening. I'm guessing hair standing up sounds more like static electricity than anything. Losing reception. Buildings, which are made of concrete and metal usually, or commercial ones, tend to absorb RF fairly well. Humans are bags of water pretty much, which tends to absorb RF well, especially at 2.4 gigahertz. There's also something called multipath, which is especially common in urban canyons where you have skyscrapers and you're down here or transmitters wherever, and that the signal will reflect off, so you might get one signal directly from the transmitter, another signal that bounces off something to you, and then that's like a bunch of reflections or multiple paths, multipath. And this can cause problems in that you'll end up with multiple versions of the signal that you'll receive, and they can interfere. That's what could be happening. I don't really know, though. It's probably one of those. Also, you could just have something in the way to when you go there, the signal is too weak. Yeah. This is 2.4 gigahertz. You're looking at Wi-Fi. So this here is a one Wi-Fi channel. It is 20 megahertz wide. Here's another one. This is probably some proprietary thing. If you look in so Bluetooth and Wi-Fi are very interesting. Wi-Fi, it says, I'm on this channel, I'm using it. It'll then say, hey, I'm going to send something. Everyone else be quiet. It sends stuff and it's done. Bluetooth frequency hops around, and it's designed so if there's interference, it goes right through it. Wi-Fi's approach to interference is it resends. Bluetooth just hops away from that fast, and that's not a problem. Bluetooth and Wi-Fi can cause problems in that Bluetooth will transmit where Wi-Fi is, and because they don't really talk to each other at all, you can end up with some interference between them. 2.4 gigahertz can be a very crowded portion of the spectrum as well. Any other questions?
The project you talked about for monitoring planes, would you call it 1090?
Dump 1090.
Dump 1090. In addition to that, is there anything else that's comparable to that to monitor anything else, whether it be satellites or?
So for satellites, the FunCube Dongle Pro Plus is interesting. It was originally designed for to use the downlink from the CubeSat thing. Balint Sieber, if you look him up, he's done some work on receiving signals from satellites. So for satellites, effectively what you want to do is either find a signal or find a satellite. Usually you'll want to get a dish to get better signal quality, point it up there, and then you want to, for that you'll probably want to buy some filters and a low noise amplifier to put right on the dish to help filter out the signal, because the satellite is way, way, way up there, and the signal can be fairly weak when it gets to you. As far as I know, there's not like, with satellites, there's not like this is software you can use to find all of them. One of the problems with satellites is they aren't always like here's everything, all the modulation data for our satellite. So a lot of it can be reverse engineering stuff yourself.
All right, do we have any other questions, right? All right, here, let me get the mic here. Here, hold up.
Are the tools that you used in this presentation linked from the slides?
No, but Google or whatever your preferred open source search engine is will fix that. Yes. I also have a page of references. Lastly, I would like to, so this is the radio data system software that I used. If you just search Google for, let's see, if you search software, I don't want to move those slides. So really the software you care about is probably GNU Radio and GR Osmo SDR, and then GQRX. If you're on OS X, you can use Mac ports to install it all for you, except for GQRX, which you can just download from, build from source or download. I didn't show that, but you can use it. But this is really all you need. Yeah. I'd also like to thank these people. Jared Boone, he did the complex number visualizer thing. Russ Handorf, or actually all these people have helped teach me about software-defined radio. Michael Osmond and Dominic Spill have done they do the HackRF, and then SCaLE for letting me speak here. Any other questions?
Anyone? Before we give them a round of applause, I guess. There we go. Excellent. Thank you again, Skylar.
You're welcome.
I guess we have a little bit of a gap here, so I don't know. You guys do whatever it is you want to do.
You can come talk to me or avoid me. The choice is yours. So now you'll see this is here. Now you see this peak here, this is this microphone. And if I turn on wideband FM. Hello? Hello? Oh, that's on as well. Or I'm just muting it. Hello? Hello? You can kind of hear, and it crashed. See if I see let's see, that's it. Hello? 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 So you can hear this here. If you notice, there is